Hello, I welcome you all. The problem reads: a girl having a mass of 25 kg sits at the edge of the merry-go-round, so her center of mass G is at a distance of 1.5 meters from the axis of rotation. If the angular motion of the platform is slowly increased so that the girl's tangential component of acceleration can be neglected, determine the maximum speed that she can have before she begins to slip off the merry-go-round. The coefficient of static friction between the girl and the merry-go-round is μs equal to 0.3. This problem is coming from the Engineering Mechanics and Dynamics 14th edition by R.C. Hibbeler. Alright, so let's begin to work. So we do have, this is going in this direction. We can simply say we have tangential to that we have here our VT, okay, and in the same direction we do have we are supposed to have our AT, but this is negligible, is equal to 0, and then we do have in that direction, okay, we have in that direction, let me use black, in that direction, that axis, we have our Fs, okay. To prevent this girl from falling off, this one is our n-axis, and then this one is our t-axis. Right, so we'll just section this so that we just redraw it. Let's redraw it here. So this is what we are talking about. So let me say I have this up to there, 1 2 3 4 5 6 7 8 9 3 maybe up to, we make it 10 up to there. All right, so this is the thickness of the merry-go-round. All right, and then let's say this is our center of our merry-go-round, so that is the z-axis. Then let's say we have the girl seated there. All right, there we go. Okay, so that's a girl. Of course, the this is going in this direction like this, a clockwise direction, and we have our tangential coming out of the screen. It's coming out of the screen. Okay, so we are not interested so much in that one. So we have the the friction force in that direction, and then we do have the normal force in that direction, and then we have the weight of this person in that direction. Let's say we also have this is our rho, which is the radius of curvature. So this is the rho, and is equal to 1.5. This is W for this scale, which is just equal to mg, and is equal to 25 kgs by 9.81. Right, and this is the normal force. This is the Fs, which is the static friction. And then we have this coordinate in this direction, which we are calling our n coordinate. Alright, so with this information we can write down our equations of motion, and then let's say our kinetic diagram. This is in this direction, and this is our MAN. So let's start with the B axis, the binomial axis, and we don't expect any movement in that direction. Right, there we go, and that is our B axis. No movement in that direction. We'll need to start in that direction so that we get the value of N, which we use later on for the friction. So say summation of forces along the B, this is just going to be equal to 0 because we don't have any motion in that direction. So this is just going to be equal to N minus W equal to 0. We know what W is. Therefore, this is just mg, which is equal to 25 by 9.81. Alright, so then we have summation of forces along the n-axis equal to MAN. AN going this direction being our reference positive. AN is the centripetal acceleration, which is just v squared divided by rho. Okay, where our rho is just equal to 1.5. Okay. Alright, and we do also have Fs, which is just equal to mu Sn, and is equal to coefficient of static friction there is 0.3, then times N, which we just found is 25 by 9.81. So we have everything. Let's just write down the equation in that direction. So we have Fs is equal to MAN. Therefore, our Fs is just 0.3 by 25 by 9.81, and this is just equal to M, and our M, you know what it is 25 kg by V. We want to find V impact divided by rho, and our rho is 1.5 meters. So we can cancel out 25 and 25 there before we even begin the calculations, and then we can say our V squared is just equal to 1.5 by 0.3 by 9.81, squaring both sides. So we are going to have this like so, okay, and this like so. Okay, therefore our V is just going to be equal to our V is equal to, this is equal to 1.5 by 0.3 by 9.81, and square root of that, then we have a 2.1 meters per second. So this is in fact the maximum. This is the maximum speed that the girl can go before she begins to sleep. So let's just outline the final solution. There we go, there we go, there we go. So I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye, and I'll see you in my next screencast.